have you ever been to the beach?
I have been to the beach.
Poured sand into a pile?
I have. I actually really am not fond of going to the beach. All that sand is messy. You end up getting sand all over the place. But
That doesn't surprise me. Well, here we are. I'm pouring sand into a pile, and of course, it's creating a cone. All right? So, let's say that I'm pouring sand onto this cone at a rate of 4 cubic inches per second. Being the math nerd that I am, I actually am pouring it at a constant rate. And I notice that the radius of the cone always is half of the height.
that makes sense. As it gets taller, it gets wider, and at the same rate. That makes sense. Okay.
Exactly. Okay. So, I want to know how fast the height is changing at a certain moment. Give me a height of the pile, Mr. Haas.
Let's say when the height is 16 inches.
Okay.
That's
so
a lot of sand.
Wow, that's a lot
Well,
of
thank
sand.
you.
So let's say when the cone of sand has a height of 16 inches, I want to know at what rate the height is changing. And I'm going to call that, and how do we say the change of the height or the rate at which the height is changing in math land?
In math land, I'm going to go dh dt perhaps.
I agree, Mr. Haas. Okay, so I'm looking for the rate at which my height is changing. I'm looking for dh dt at this instant in time when the cone is 16 inches high. All right, it's a related rates problem. We've been doing this, so we should feel pretty confident with this. As you know, we always look for a formula, an equation that relates to variables. Well, I know something about volume. I know something about I'm wanting to find something about my height. So I'm thinking the volume of a cone problem is going to work for us, right?
Sounds good.
So volume of a cone is a third, as I'm sure all of you know, a third of the volume of a cylinder. Volume of a cylinder is just pi r squared, the circle, times the height. Here's the volume of a cone. Okay? So if I want to find the rate at which my height is changing, I'm going to have to take the derivative, right? But hold on, Mr. Haas, why do you know this? What's confusing?
I don't know. We got looks like an extra variable in there that we don't even need.
Yeah,
We
I've
could
got
get rid of that
radius
somehow.
in there. If
I
I
don't
take
know.
the derivative now, I'm going to have to do the product rule, and then I don't know anything about radius. The rate is changing. I have a great idea. I think you're thinking it too, Mr. Haas. Can I just substitute something in for that radius?
I'm thinking you can. As a matter of fact, you wrote the radius is half of the height of the cone, and that's a constant, and that's kind of nice. I mean, that generally works with cones. I mean, actually, that always works with cones.
That's
I'm gonna
right.
say.
That's
That
right.
the ratio of the height to the radius is always going to be constant as you're filling up a cone.
Fantastic. So can I just do a little substitution here and replace that r with 1/2 h, so I just have one variable over here? All right, I'm doing it, Mr. Haas. What do you think?
Go for it.
1/3 times pi times my radius, which is half of the height, squared times height. So I just replaced that r, I substituted that r. Here is my new equation for the volume of this particular cone. Let's just clean this up a little bit. 1/2 squared, of course, is 1/4. H squared times h. It's a whole blob of things multiplied together. So my volume is, well, let's see, 1/12, I'm thinking,
Looks good.
times pi, h squared times h to the third. I'm feeling much better about taking the derivative of this.
Looks good to me.
All right, let's do it. Let's take the derivative. Take the derivative of each piece. Derivative of volume with respect to time is dv dt. I'm looking to see how my volume is changing over time. I only have one term over here, so let's just do the power rule and the chain rule. So 3/12, brought that exponent down, pi times h squared times the derivative of h with respect to time, dh dt. Took my derivative. Let's substitute it in what I know. Let's see, do I know dv dt, Mr. Haas?
I think you do.
Ooh, I do. That was my given information. That's a 4. 4 cubic inches per second. 3/12. Can I just write that as 1/4?
Let's call it 1/4.
All right, good. Pi. Do I know the height at this moment?
You do. It is 16.
Fantastic. Squared. And dH/dt, well, that's what I'm looking for. So that's my unknown. All right, so let's see. 16 squared.
Well, that's 256.
Okay.
And I'm gonna.
Times 1/4.
That gives you
Probably
64.
Figure that out. Thank you, Mr. Haas. Okay, now I'm just trying to get dH/dt by itself, so I'm going to divide both sides by 64 pi. I don't know why I felt the need to grab another color, but it's just kind of
Looks
fun.
good.
Thank you
I'm
for your
enjoying it.
support. All right, so I have dH/dt, that's the rate at which my height is changing, is 4/64. Can I just call that 1/16 times pi?
That sounds great.
Hey, I think I'm done. Did I just find the rate at which my height is changing?
That is it. And you want me to just see what it would be if I actually
Sure,
calculate that, put in
let's see
pi
that.
there? I have
Pretty small
1 over
number.
the quantity 16 pi. I have 0. This is not going to be a big number. 0.0199. I'm rounding a little bit there.
That's fine. And my units would be, let's see, inches per second.
So wow, I mean, you can see that as the cone gets bigger and bigger. I mean, 16 inches. That's a pretty tall cone.
That is.
You're only adding to it at 4 cubic inches per second. That height's not changing very fast.
It's not changing very fast.
I bet at the bottom it would change pretty fast.
I think it
I
probably
think it
would.
probably would.
Thanks for your help, Mr.
That's
Haas.
fabulous, Mr.